All right, page 6. So remember, with related rates, we're always going to be starting off with some algebraic or geometric equation. And then once we have that set up, then we move into our derivative, our related rates derivative process. So let's read the problem here. It says volume of a cube. If each edge of a cube is increasing at a constant rate of 3 centimeters per second, how fast is the volume of the cube increasing when the length of the edge is 10 centimeters? So let's talk about a cube here. What do you know? What's the formula for volume of a cube? It's length times width times height. But what do you know about length, width, and height? All the same. So I'm going to use x to represent the length, width, and height of the cube. So it's simply x cubed. Right? Length, width, and height all being the same variable. So anytime we're dealing with related rates, I always like to start off with building the derivative, and that way I'm just done with the calculus, and also I can see all the variables that is going to play a role in the problem. So let's just find the derivative. So v becomes, what's v's derivative? Yep, dv over dt. Every variable gets touched on by time. Every variable gets impacted by time, but we usually just do power rule first for that variable, and then we attach a d over dt. Okay, x cubed becomes, yeah, simply power rule, but here we're asking for x's derivative with respect to time, so times, yeah, dx over dt. Okay, so that ends the calculus portion, and now we're just doing a bunch of substitutions to try to get and solve for that variable. Okay, let's go back and reread the problem. If each edge is increasing at a constant rate of 3 centimeters per second, well, we know edge is related to x, but it can't just be x, right? Because you see all these movement words there, increasing, rate, centimeters per second. So what do you think the 3 will be assigned to? Yeah, dx over dt. So we'll say dx over dt. Positive or negative? Because increasing, yeah. So there's always going to be context clues within the problem that's going to tell you, am I going to keep my rate positive, or am I going to have to adjust my rate to be negative? When the length of, how fast is the volume of the cube increasing? What are we looking for? Good. You see V, so you know it's definitely volume, but it can't be a static value because there's all these movement words, right? Fast, increasing. So that means it's going to be dv over dt. Now, even though we don't know what the value for dv dt is, what do we expect this number to be? Positive or negative? Positive, right? You can imagine that as the length is increasing, that your volume is going to be growing. It's not going to be decreasing. Okay, when length x of an edge is 10 centimeters, so that's just x. Okay, do we have enough to solve for dv dt? Yes. Yes. Okay, go ahead and plug in, and let's find that value. Yeah, you can bring it up here. I can charge it. Thank you so much. Okay, let's talk about units here. We want volume and time over each other. So volume is in terms of centimeters cubed per second. All right, number 10. If the radius of a sphere is increasing at 1 centimeters per second, find the rate of change of its volume when the radius is 6 centimeters. So again, anything with sphere or cones or cylinders, those formulas we provided for you. There's no need to memorize these. Okay, let me help you through the derivative and then see if you guys can finish the problem. Okay, so V becomes, yeah. We know 4/3 pi is not going to go anywhere, right? That's just some number that's hanging out in front. It's really just r cubed that's really getting impacted here. R cubed becomes times the, yeah, dr pt. Okay, let me just clean this up here and then see if you guys can figure out how the rest of the pieces fit. So the threes can cancel out. I'm going to just make this 4 pi r squared. Okay. Any questions so far? All right, see if you can read the problem and start assigning the values they give you to variables and try to also figure out what variable that they're trying to get you to solve for. And then you can plug everything in and solve for your missing variable. And then, yeah, see if you can also find your units of measure as well. All right, let's see how we did. Radius of the sphere is increasing, so you know that's dr dt. There's all these movement words. It's got to be a time component with radius, so dr dt. Find the rate of change of the volume, so you know you're looking for dv dt. When the radius is 6 centimeters, that's enough to plug everything in. I got 144 pi. I would prefer to leave it in that form. I think maybe the only time that you would want to get into a decimal is if it was like a multiple choice question. They're trying to get you to match with one of their choices. If that's the case, then use the decimal version. Units of measure, volume is cubic centimeters, time is seconds, so cubic centimeters per second. Any questions? Okay. 22. This, we haven't talked about this shape yet. This is a cylinder. So let me just for visual purposes here, I just want to compare a cylinder with a cone because the formula looks similar, but there's going to be very different applications here. So first you have a cone here. If you don't want to write this down, you don't have to. Just want to show you something real quick here. Sorry. R for 3, r squared. And again, these formulas we provided for you, but I just want to show you something here. So the problems that we're going to see involving cones and cylinders is usually with some liquid or water in the cup or the tank that is either rising or falling. And cones and cylinders, sometimes we associate these with each other because their formulas look very similar. and also we see that the water level inside these containers take on the shape of what we're dealing with, right? So here, the water inside the tank is forming its own cone. Here, the water inside the cylinder tank is forming its own cylinder. Now, here's a big difference, though. As the water level is rising and falling, what's happening to the radius and the height of this water cone here? They're both changing. Okay, so that's why our problem has been so challenging. That last one before the weekend on Friday, we're going to practice more with that. It's the most challenging part because both your R, and your H are variables. They're both changing. So keeping track of both those variables requires a little bit more effort. But here, cylinder, so look at the water level or the water inside this tank here. As the water level is rising and falling, is the height changing? Yes. Is the radius changing? No. So here, for the cylinder problems that we're going to see, your radius is a constant. And that's why our cylinder problems should be a lot easier, because as soon as we know what the radius of the container is, we're going to insert that radius into the formula for the water tank, for the water inside the tank, because that radius is never going to change. If that value is never going to change, there's no need to hold on to a variable. We only want to hold on to a variable if we realize that there's, if it's ever changing value. So that means for cylinders, there's no similar triangles. There's no proportions, and it should be a lot easier. We should be able to just jump directly into the derivative as soon as we replace the radius. Okay, so here, water is flowing to a vertical cylindrical tank, diameter 6 centimeters, a rate of 5 cubic meters per minute. Find the rate at which the depth of the water is rising. So here we have our diagram. Water inside the tank. The diameter is 6 meters. And our formula. So at the very beginning of the problem, we already know that we don't want to confuse this with cone problems. We already know that the radius is a constant. What's the radius? 3. So as soon as you know what the radius is, go ahead and get rid of it. There's no need to hold on to that variable. And the nice thing about cylinders is that as soon as you make that substitution, you're ready to find the derivative. There is no need to do any proportions, any of the steps that we did for cones. The derivative should be ready to go. Okay, so let's go ahead and do that. V becomes
V over T.
Yeah. 9 pi stays. H becomes
H over.
yeah. And now we're just ready to do our substitution steps. Water is flowing into the tank at a rate of 5 cubic meters per minute. What's that?
H over.
V, right? EV/dt. Cubic centimeters, that's a volume related value. Find the rate at which the depth of the water is rising.
Yes.
Yep. Now we can plug in. Notice pi is left in the denominator if we're trying to isolate the HDT, and we can't let that pi move up to the top. It needs to stay in the denominator there. Otherwise, you're changing the value. So on the one hand, cylinders feel easier, but we're going to be doing more problems with cones because it just takes more effort. So most of our efforts are going to be put into cone problems. And so in a way, cylinders are easier, but then it's also harder because sometimes students get so used to that cone setup that they also apply it for cylinders, especially when the problem is providing information to see if they can get you to use cones. And so sometimes what happens is this: they start giving you extraneous information. They start saying you, oh, the height of the container is 9 meters, and the height is going to be 4 meters, and they give you all this extraneous information, and you feel like you have to use it, and so students start putting them into the cone structure, and then they go down the wrong path. Okay, so so cylinders are easier, but it's also more challenging because you really have to kind of stay disciplined and know, okay, all right, they're just trying to distract me. I know my radius is constant. I get that radius to go away, and I can just find the derivative. I can ignore all this additional information that I don't need. Okay. So, okay. Now, any questions with cylinders? Let's go back to cones. Requires the most amount of practice, so we need that time to get used to it. All right, a container in the form of a right circular cone. Here's our formula: V equals pi over 3 r squared h. Radius is 4 meters, height is 60 meters. See the figure above. So as soon as you see cones, I'm just going to go ahead and start building the structure that I need. So I only care about this portion of my diagram there. So I'm just going to just draw my own. I know that the larger triangle represents a container. The smaller right triangle represents my water level, the smaller cone. Okay, radius 4. Sometimes they may give you radius, sometimes they may give you the diameter, so just adjust accordingly. So your first step is just trying to get that proportion equation up and running. So I'm going to say small radius is to big radius as small height is to big height. Cross multiply. Still don't know which variable to solve for, but I'm ready to solve for it as soon as I gather more information. Okay, water is being poured into a container at a constant rate of 16 cubic meters per minute. I don't see that variable yet, but what is that talking about?
dV.
Yeah, dV dt. Positive or negative? Positive, yeah. Water is pouring in. My volume is increasing. How fast is the water level rising? dHdt. That's what's unknown, right? When the water is 8 meters deep. H equals 8. Okay, so let me talk about these two here. Whatever we're looking for is going to help guide our equation. Okay, if we want dHdt, you prefer to get your volume in terms of H because H is related to dHdt, and H will produce a dHdt better than R can. So this is going to tell us that we want our volume equation in terms of H, right? We want that dHdt to show up, and H variable will just naturally get that dHdt. The second important thing here is that we don't want to touch this value, right? So do not use until after derivative. And the reason, again, that we don't use this value is because this 8 is talking about the height level of the water, which is a moment in time. But we know that this problem is we're still wanting to hold on to that h variable because we want to build the formula around the fact that h is still a variable. But once we find the derivative and we have everything set in stone, then we can work that 8 in. But if you put that 8 too soon, you lose the h. If you lose the h, you're not going to be able to produce that variable that you want to come out of the derivative. So now let's go to our volume equation. And so what variable do we want to try to get that we want to try to solve for here? R, yeah, because you want to find a replacement for R. That's why you want to solve for R. So R is equal to 4h over 16. R is equal to h over 4. So this is going to help us build or make our substitution into our volume equation. A lot of sometimes students struggle with the fact that they just want to do the derivative and they start producing dRdt, dHdt when the algebra steps are not set up yet. So make sure that after you make your substitution that you're still doing a lot of cleanup. There's quite a few things you got to do before you do the derivative. So even at this stage, we still want to figure out a way to get all the numbers to combine together. All the variables need to combine together. If you have multiple h's everywhere, you're not ready for power rule. So make sure that you can recognize when an equation is ready for you to move on to the derivative. So now we're ready, right? The coefficients have come together. We're only down to one variable, and this variable raised to a power. So this is nice and clean. The derivative should be more straightforward here. So all we need is power rule. Okay, so do our derivative, v becomes dvdt. Pi over 48, that's not going to go anywhere. That's just going to be a coefficient. H cubed, 3h squared, dH/dt. Now you're ready. Now everything is fair game. You can now plug in anything that you want. The dV/dt is 16. H is now 8. Now you're ready for that 8. And then now you're just working to find a way to get that dH/dt to solve. Thank you. So I'm just moving that fraction over to the other side. I know dividing by this fraction is the same thing as multiplying by the reciprocal. And as you put all this number in your calculator, leave pi out of it. Just know that you're going to have to attach a pi at the end to the denominator of your fraction. So 16 times 48 over 192 just becomes 4, but the pi stays below. Okay, 35 is Pythagorean theorem problem. Let's skip that one. We can come back to it later. I want to show you the last major type of problem, and that is it's a similar triangle problem, but it's a very specific type of similar triangle. We call these are shadow problems. We've seen this show up on the AP exam, so we need to make sure that we go over it. Okay, so go to page 8. So this one will be the last of the new types of related rates. There's still something called trig related rates, but we're going to save that for end of semester when we look at when we have a trig unit and we look at all the different types of problems from the trig perspective. So let's go to page 8. So this is also similar triangles, but it's gonna, at least algebraically, it's gonna feel easier than cones, but it's very specific in the way that we set up. So let me read this problem here. So a man is 6 feet tall. So this person here is representing he's 6 feet tall. He's walking away from the lamppost at a rate of 5 meters per minute. So the distance between him and the lamppost is changing. So that change is represented by x. And at the same time, the lamppost is shining down and is causing the length or the shadow to create past the person. And the tip of the shadow is going to basically create that triangle within a triangle. Okay. So you got one triangle formed by the tip, the person's height, and the base. And the second triangle is tip of the shadow, top of the lamppost, and the bottom of the lamppost. So triangle within a triangle. We're always going to set it up this way: x and y, and then person's height and the height of the lamppost. How fast is the shadow growing when the person is 30 feet from the lamppost? How fast is the tip of the shadow moving when the person is 30 feet from the lamppost? So we're going to set up similar triangles, and we're going to say this. We're going to say the height of the small triangle is the height of the large triangle, so 6 over 20, as the base of the small triangle is to the base of the large triangle. So in this case, what represents the base of the small triangle? Yeah, y. And the base of the large triangle is going to be x plus, yeah, x, not xy, x plus y, yeah. We don't want to multiply these together. Make sure that you're adding your two lengths together to get that full length. All right, so this is the equation that we're going to find the derivative for. But if we just cross multiply, we can basically eliminate all the fractional portion of it. So I'm just going to cross multiply and distribute. Combine like terms, all my fractions are gone. I'm just able to move terms together, combine like terms together. So I'm going to subtract that 6y to the right side. 20 minus 6 is 14. Find the derivative. Now, remember, this is related rates here, so every variable is going to get impacted by time. So we're ready to find the derivative. There's no separate equation we got to substitute into. This is the equation we're working with. All right, 6x becomes 6 dx dt. And then 14y becomes 14 stays, but y becomes what?
You are.
dy dt. So this is the equation we're going to be plugging into and finding our data. So let me talk about what these rates mean. So dx dt represents how fast the person is moving away or towards the lamppost. So basically the rate of the person walking. dy dt, as the person is moving away and towards, the length of the shadow is going to be changing. So it's going to be rate of change of his shadow length. And finally, the tip of the shadow, it's going to be moving the fastest. So as a person is walking and the length of the shadow is increasing, that tip of the shadow is going to be impacted by both of the rates. So if we add the two rates together, that's going to indicate how fast that tip of the shadow is moving. So the problem says the person is walking away from the lamppost at a rate of 5 feet per minute. So what do you think we can assign that to?
Dx.
Positive or negative?
Negative.
It's actually positive. Why is it positive?
Moving to the right.
Not to the right.
Away from.
Yeah.
This.
Yeah. What's happening? If you're walking away from the lamppost, what's happening? Yeah, that length is increasing, right? If you're getting further and further away from the lamppost, your x is going to be increasing because that length is going to be getting larger and larger. So we want it to be a positive 5 for our dx dt. So let's go ahead and put that down. Dx dt is positive 5. How fast is the shadow growing? What are we looking for?
dy.
Yeah, dy dt, that's the unknown. When the person is 30 feet from the lamppost. What's that? X is 30. Okay, so we're going to just put 5 into dx dt and solve for dy dt. So divide to solve for dy dt, I'm just going to divide by 14. Do some reducing. I get 15 over 7. That's just going to be some decimal value, but you can leave your answer in that fractional form. So 15 over 7. That's part A. That's the rate of the length of the shadow changing. And then finally, how fast is the tip of the shadow moving? So now we just add the rates together here. We have both rates, right? We have the person walking plus the rate of the length of shadow increasing. We add those together. You can use your calculator or do common denominators. Oh, sorry. Yeah, it's per minute. Okay. Okay, what information do we not use? Yeah, so this is extraneous information. We don't need that because the derivative doesn't need that to get from one rate to the other. So it doesn't matter how far he is away from the lamppost. That rate is not going to change depending on his distance. So there is going to be some extraneous information in this problem, and that's going to be the x. We don't want to insert that x at the beginning because we know that we want to hold on to that variable. So as we build our equation, we don't want to be plugging in that 30 at all. Okay, any questions here? So I'm going to start you off with a diagram. Your diagram is always going to start off this way. Okay, and then go ahead and fill out the person's height and the height of the lamppost, and then go ahead and do the rest of the problem. So be the exact same setup, exact same format. Just want to see, have you guys try an example on your own to kind of help solidify the steps for you. So try to from here.
You had 5. Was that? You just had the EX.
Oh, how no is a positive five? B, okay.
Part B, why did we have 5 again? All the way on like the right, like just how you got 5 plus the EX.
Oh, okay. Yeah, so part B, we add these together because we're doing, yeah, GXP plus DYDT is tip of the shadow.
Thank you.
Yeah. So for number 2, I would solve for B before I solve for A, because B is the length of the shadow and then A is the 2 rates added together. So feels a little backwards here. So number 2, I would do part B before I did part A. Notice that now the person's walking towards the lamppost, so that means dxdt is what? Negative. That distance is decreasing between the person and the lamppost, so we want that rate to be negative.
For anything, you have to put it in the decimal.
No, you can do it as a fractional form. Yeah. But they're both going to be negative. Yeah. Negative 7.5 for A, negative 2.5 for B. Okay, we did the top of page 9, right?
Yeah.
Okay, let's do the bottom of page 9 here, number 4.
We started it, but we only got to.
Oh, we didn't finish it. Okay, all right, so let's see if we can revisit page. Let me yeah, top of page 9. Let's see if we can continue working on that problem. Back to a cone problem. I'll leave this up here for another moment if you're still looking at it. Okay, anybody still need to look at page 8? No. Okay. So we set up initially the same way here. But the difference here is that we're looking for dr dt. And this is an indication as to how we want our volume equation to look. We would like our volume equation in terms of R only, so that it can produce a dr dt, which means we need to find a replacement for H, which means that H equals 2R. And again, we have some information, data about the height of the water level that we're not going to use until the end. So after you clean up, this is where we need to be before we start to apply our derivative step. Okay, from here, derivative. Two pi over 3 stays. R cubed becomes 3R squared, dr dt. Do some cleanup. Okay, I think we're ready to start inserting information. dv dt gets replaced with -80. We're looking for dr dt. That shows up. That's good. But there is something, though, that we need to do some adjustment, because they're giving us the height of the water level, but we want the radius of the water level. How can we resolve that issue here? Do we have something that can help us get from the height to the radius of the water level? Is there a conversion that we can use? All right, good. 2R equals H, right? So if we know that 8 is H, I can plug 8 in for H to try to get that radius of the water level. So my radius is going to be 4. $80 and 32 can reduce. You don't have to, but just make sure that your pi stays below. Any questions with cone problem here? Okay, let's go to bottom of page 9. Cylinder problem. Formula looks a lot like cone, but what's nice about cylinder problem? Radius is a constant. So as soon as you know what the radius of the water level is, replace that into the volume equation, and we can jump directly into the derivative. Should be a lot faster. There's no similar triangles. Okay, what's the radius going to be? 5. So as soon as you know what the radius is, go ahead and make that substitution. You should be ready to jump directly into your derivative step. Oops, sorry, 5, right? Sorry, 3. V becomes dV dt, 25 pi stays, H becomes dH dt. Okay, we're ready to start plugging information in. Let's gather some information here. Let H be the depth, okay. The volume is changing at a rate of negative 5 pi root H cubic inches per second. What is that assigned to be? Find dH dt. They don't give us the H value, so that means our answer is going to contain H in it. But we can start plugging in, right? dV dt gets replaced with negative 5 pi root H. We're looking for dH dt. Pi's cancel out. 5 and 25 reduces. 5 stays below. I don't have a number to plug in for H because they don't provide that for us. And what's our units going to be? Well, it's height. So height is just what? Just inches, yeah. So only time we have cubic is volume. Only time we have squared is area. Any other variable is just going to be single, just one dimensional. If it's height or radius or length. So just inches per second. Okay, let's turn to page 21. Sorry, 20, page 20. So your homework is just going to be these 2 cone problems, but I think we have 5 minutes to get started. So just page 20. This will be your homework, just 1 and 2. And let's just see if we can make some progress in the first 5 minutes, the remaining 5 minutes. Sorry?
Radius.
Yeah, you want to solve for radius. That we're asking, yeah. Mhm. What variable are we trying to solve for? Yeah, dropping. So water level dropping, that's talking about the HDT. So this is the hint that we want to use here. This is going to help guide our volume equation. We want H, which means we would like the R to be replaced. Okay, your homework, just page 20. 1 and 2, I'll send out a reminder this afternoon.
Just reading. We're gonna get our test back.
I'm almost halfway through. I think I'll be done by Thursday. Yeah.
Thank you.
Mhm. Thank you. Good day.
It is.
Really easy.
Thank you.
Thank you.
Question about this.
Uh-huh.
Well, if we're given this, will we always be given this?
Well, it's always going to be this relationship if you set it up this way.
Okay,
Yeah,
so just like memorize.
Just
that.
memorize it. Yeah.
Because this like applied to here.
Mhm.
Okay, and then I got the first 2 pages of homework done.
Okay, sure. Okay,
But I feel like
great. I'll mark it down. Thanks, Dan. Uh-huh.
yeah, I put this on your-
Thank you.
Yeah, I would, I'm.
Thanks.
Are you putting it?